Oceanography News.
The stars above me are closing in, so water roll me home. Day will come, but night is long. The siren song still calls me young. The fading candle is growing dim, so water pull me in.
Knowledge of the oceans is more than a matter of curiosity. Our very survival may hinge upon it.
In this week's Ocean Marine Science News, our first story is Satellites Spot Rapid Doomsday Glacier Collapse out of the University of Manitoba. 2 decades of satellite and GPS data show the Thwaites Eastern Ice Shelf slowly losing its grip on crucial stabilizing point as fractures multiply and ice speeds up. Scientists warn this pattern could spread to other vulnerable Antarctic shelves. Thwaites Glacier in West Antarctica, widely known as the Doomsday Glacier, is changing more quickly than almost any other ice ocean system on the planet. Its future behavior remains one of the biggest unknowns in forecasts of global sea level rise. One part of this system, the Thwaites Eastern Ice Shelf, TEIS, floats on the ocean and is partly held in place by a pinning point at its northern edge. Over the past 20 years, this shelf has developed increasing fractures around a major shear zone located upstream of that pinning point. A new study published in the Journal of Geophysical Research, Earth Surface, AGU 2025, offers the most detailed account yet of how this slow breakdown has unfolded. The research was produced at the Center for Earth Observation Sciences and led by Debangshu Banerjee, a recent graduate student from the Center for Earth Observation Science, along with Dr. Karen Alley, Assistant Professor, CEOS, and Dr. David Lillian, Assistant Professor, Indiana University Bloomington, and former research associate at CEOS. Their work contributes to the TARSAN, Thwaites Amundsen Regional Survey and Network Project, one of the programs within the International Thwaites Glacier Collaboration, ITGC, a major US-UK effort to understand the forces driving change in the Thwaites Glacier. Several well-known glaciologists, including Dr. Ted Scambos, Dr. Martin Truffer, Dr. Adrian Luckman, and Dr. Aaron Peltit, also contributed to this research. Fracture growth, ice dynamics, and a strengthening feedback loop. Using 20 years from 2002 to 2022 of satellite observations, ice flow speed measurements, and in-situ GPS data, the team documented how fractures within the TEIS shear zone formed and evolved. Their analysis shows that the gradual growth of these fractures weakened the shelf's connection to the pinning point. As this attachment deteriorated, the ice upstream began to flow more quickly, reducing the shelf's mechanical stability. The researchers identified 4 clear stages in this weakening and highlighted 2 major findings. The first is that the fractures expanded in 2 distinct phases. Long fractures aligned with the direction of ice flow appeared first, followed later by shorter fractures that cut across the flow. The second is evidence of a positive feedback cycle, in which these fractures increased ice acceleration, which in turn caused further damage. This accelerating loop played a significant role in the shelf's recent decline. Our next story is a mystery, the mystery of the missing deep ocean carbon fixers. A UCSB study reshapes understanding of deep ocean carbon storage with implications for long-term climate stability. In a step toward better understanding how the ocean sequesters carbon, new findings from UC Santa Barbara researchers and collaborators challenge the current view of how carbon dioxide is, quote, fixed, unquote, in the sunless ocean depths. UCSB microbial oceanographer Alison Santoro and his colleagues, publishing in the journal Nature Geoscience, present results that help reconcile discrepancies in accounting for nitrogen supply and dissolved inorganic carbon, DIC, fixation at depth. Quote, something that we have been trying to get a better handle on is how much of the carbon in the ocean is getting fixed, unquote, Santoro said. Quote, the numbers work out now, which is great, unquote. This project was supported in part by the National Science Foundation. So, who's doing the fixing? The ocean is the Earth's largest carbon sink, buffering us from the worst that climate change can throw at us by absorbing a third of our carbon dioxide emissions, which in turn regulates global temperatures. We rely heavily on the ocean for this phenomenon, which is why it's important to fully understand the complex processes that enable it. Quote, "We want to know how carbon moves around the deep ocean, because in order for the ocean to impact the climate, carbon has to make it from the atmosphere to the deep ocean," unquote, Santoro said. In the ocean, the majority of this inorganic carbon fixing work is conducted by microbes. Phytoplankton, a group of single-cell organisms that take up inorganic carbon dioxide, including dissolved carbon dioxide gas, at the ocean's surface are known as autotrophs. They produce their own food in the same way plants on land photosynthesize carbon dioxide and water, producing organic matter, sugars, and oxygen. The prevailing idea is that while most DIC fixation happens in the upper sunlit layer, thanks to photosynthetic phytoplankton, a significant amount of non-photosynthetic DIC fixation also occurs in the dark layers of the ocean. An assimilation dominated mainly by autotrophic archaea that evolved to oxidize ammonia, a nitrogen-containing compound for energy rather than sunlight.
I'm simply saying that life finds a way.
Woodsole Oceanographic Institution researchers are turning up the stereo on Maui reefs, and baby corals are showing up to the party. Playing the sounds of a healthy reef can encourage coral larvae to settle, potentially reversing the decline of vulnerable reef ecosystems. You can see the full story on CNN by following the links in the description of this video. Using music to heal coral reefs makes it seem like Nikola Tesla might have been onto something when he said, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration."
Beneath the waves, we often picture a quiet stillness. But if you listen closely, the seafloor is bustling with crackles, chirps, and pops.
A healthy reef is really just vibrant with sounds. You can actually hear fish calling to each other, so that might be parrotfish scraping on the reef or attracting mates or defending territories.
Erin Mooney is the principal investigator of reef soundscapes and biodiversity at Woods Hole Oceanographic Institute in Massachusetts.
We started listening to reefs really in the Virgin Islands in about 2012. The focus of that was how to really understand or use sound to measure the health of reefs.
Over the last few months, Aaron and his Coral Reef Solution team have been conducting a field study on the reefs around Maui, Hawaii.
We're gonna go pick up the surface buoy first, and then we'll suit up.
But they're not here to listen. They're here to play their own symphony of reef noises, to test if it can spark new life on decaying areas.
When you lose these reefs, you begin to kind of lose the vibrancy, the sound cues, or the sense that might attract those baby fish and baby corals back to the reefs.
The next story comes out of Antarctica again. Southern Ocean might be gearing up for a thermal burp that could last a century. When humans manage to cut enough emissions and eventually reduce global temperatures, new research shows the Southern Ocean could kick warming back into gear. Consider your morning cup of coffee, which I need a refill on as recording this. Your kettle's heating element, or flame on a stove, warms up water that you infuse with beans and pour into a mug. Maybe you get busy and the cup of joe sits there for a while, releasing its heat into the atmosphere of the room, until it reaches equilibrium with the indoor temperature. In other words, it got cold. Now consider that expansive Southern Ocean, which wraps around Antarctica, could one day do much the same thing. Since the Industrial Revolution kicked off, humans have dialed up the kettle to its max, adding extraordinary amounts of heat into the atmosphere, more than 90% of which has been absorbed by the sea. It's also taken up a quarter of our CO2 emissions. Under climate change, the Southern Ocean has been storing warmth which, like your morning jolt, can't stay there forever, and will someday return to the atmosphere. New modeling suggests that this burp of heat, the scientists called it that, by the way, could be abrupt. In a scenario where humanity eventually reduces its greenhouse gas emissions and then goes net negative, Finding ways to remove those planet-warming pollutants from the atmosphere, global temperatures fall, but suddenly the Southern Ocean belches its accumulated heat, leading to a rate of planetary warming similar to what humanity is causing right now. And the thermal burping would continue for at least a century. Put another way, according to this modeling at least, humans figure out a way to reverse climate change, only to see the Southern Ocean essentially restarted. While there would be nothing our descendants could do to stop this, since the warming would be driven by already stored heat, the calculations are yet another urgent call to reduce that pollution as quickly and dramatically as possible. The sudden eructation is not a sure thing, however. It's the prediction of a model, but it's a step toward understanding how the planet could respond as humans continue to manipulate the climate, both warming and cooling it. The question is, how will the climate system, and specifically the ocean, react to scenarios where we remove CO2 from the atmosphere, and when we have a net global cooling effect? Said Sevna Frey, an oceanography PhD student at Germany's Geomar Helmholtz Center for Ocean Research, Kiel, and co-author of the paper. Southern Ocean may encircle the frozen continent of Antarctica, but it's very effective at storing heat. It alone holds around 80% of the warmth that's taken up by all the oceans. Some of this comes from currents that transport relatively toasty water south, but also lots of upwelling in the Southern Ocean brings cold water to the surface to be warmed up. The skies above the Southern Ocean are also somewhat less reflective than elsewhere around the globe. Cargo ships and industries in the northern hemisphere spew air pollution in the form of aerosols, which themselves bounce solar energy back into the cosmos and help brighten the clouds, which reflect still more. That cooling phenomenon has vied, in a sense, with the warming that's coming from the burning of fossil fuels. The competition hasn't been as prevalent over the southern hemisphere because this slightly more pristine atmosphere, said Rick Williams, an ocean and climate scientist at the University of Liverpool who studies the Southern Ocean but wasn't involved in the paper. In the scenario the researchers modeled, the atmospheric concentration of CO2 increases by 1% every year until the total amount is double what the planet had before the Industrial Revolution. The negative emissions technologies reduce the carbon concentration by 0.1% annually. The study didn't look at specific techniques, but one option is direct air capture of CO2, though this remains expensive and limited in scale. In response, the atmosphere, land, and oceans cool. But something starts brewing in the Southern Ocean. Its surface becomes colder, but also saltier, due to the formation of new sea ice. When seawater freezes, it rejects its salt, which is then absorbed into the surrounding waters and makes the surface layer heavier. At the same time we have these warm, deeper waters, Frey said, at some point the water column becomes unstable, and that's when we have deep convection event. In other words, a burp. It's just one way that our planet's extraordinarily complex and intertwining systems might respond to rising and falling emissions in the centuries ahead. Quote, there's a very large uncertainty in the Earth system response to net negative emissions. We don't understand that very well, unquote, said Simon Fraser University climate scientist Kirsten Zickfeld, who studies these dynamics but wasn't involved in the new paper. Quote, we may well encounter surprises along the way, as this paper shows, unquote. To be clear, in this scenario, removing atmospheric carbon significantly reduces global temperatures. Even factoring in the burp, and the faster we move away from fossil fuels, the less CO2 we'll have to remove down the line. Doing negative emissions and reducing our carbon load in the atmosphere is a good thing, Williams said. I would just add that rather than do negative emissions, it's better not to do positive emissions in the first place. This video is a superb NASA animation of the AMOC, the Atlantic Meridional Overturning Circulation, and also includes the whole thermohaline ocean circulation, also known as the Great Ocean Conveyor Belt, and it shows just how intertwined our planet really is. You can see as the warm water from the Gulf Stream goes across, it then sinks once it gets cold because cold water sinks, and then it flows back down south underneath the warm water. The AMOC then flows down towards Antarctica and connects to the rest of the Great Conveyor Belt of the ocean. On a side note, D2 Inc. will be exhibiting at AGU 2025 in New Orleans next week from December 15th to December 19th. I will be there in person, and along with our sales manager, Jake Soares. We hope to see you there in person. This is a floor plan for the show. It's an absolutely massive venue. We are booth 413, and we'll have giveaways like D2 water bottles for people that stop by. Our booth should be very easy to find. You walk in from the front entrance, go past about 3 booths, and then we're right there on the left, booth 413, and we hope to see you there at AGU next week. After you're done watching this video, make your way over to d-2.com. You can also find the link in the description box for this video, and check out our news page, and make sure to bookmark it so you never miss an update from D2 Inc.
Knowledge of the oceans is more than a matter of curiosity. Our very survival may hinge upon it.